This is problem 36 from the electric force. In many applications, oppositely charged parallel plates are used to suspend charged particles. Imagine an oil droplet of radius r and mass density rho sub m. This is to distinguish the mass density, which we have not been using, from the charge density, which we have been using. So they're suspended between the plates. The plates have a charge density sigma, that's a surface charge density, and the bottom plate is positive. And in part A, we want to determine the charge on the oil droplet as a function of its mass density, its radius, the charge density on the plates, the gravitational field strength, and the permittivity of free space. So there's a specific reason why they are giving us the radius r and the mass density rho sub m, and that is because this problem is actually an illustration of Millikan's famous oil drop experiment. And you could actually, by looking at the oil droplet, if you had the appropriate devices, you could measure the radius of the oil droplet. And if you know the mass density, that would allow you to find the mass of the oil droplet, which is what we are really concerned with. The way the experiment works is you spray some oil droplets into the space between the two plates, and when you spray the oil droplets, you have no way of knowing what the mass of these different oil droplets are going to be, and you can't really measure the mass of all the different oil droplets, but you can, by looking at the droplet, you could measure the radius. So we're going to come back and talk about what was shown in the experiment in just a minute, but first we're going to solve the problem. So the oil droplet is suspended between the two plates. This is the one problem in which we do have to include the force of gravity along with the electric force, and the reason for this is if you only had the electric force, the particle would move and it would not be suspended. So for the particle to be suspended, we must have at least one other force, and it must act in the opposite direction if the net force is going to be 0. The bottom plate is positive. If the bottom plate is positive and the top plate is negative, the electric field points this way, and the electric field will point in the same direction as the electric force if this particle is positively charged. We know that the force of gravity is going to act downward, and I'm going to assume downward is towards the bottom of the page here, which means I need the electric force to be acting upward. If the electric force is acting upward, the charge here on the oil droplet must be positive so that the electric field is pointing in the same direction as the electric force. I want to find the charge on the oil droplet. I've already determined that it's a positive charge, so I don't really have to worry about the signs here. I can just focus on the magnitude, and I know it's going to be a positive charge. So if the charge is suspended, these two forces must be equal to each other. So the electric force is equal to the force of gravity. And the electric force is equal to the charge times the electric field. The gravitational force is equal to the mass times the gravitational field, which is little g. And if you're close to sea level on Earth, little g is equal to 9.81 meters per second squared. We need to know E, but remember from our previous example problem, when you have parallel plates and you have a charge density of sigma on both plates, the electric field between the plates is equal to sigma over epsilon naught. So this becomes Q times sigma over epsilon naught. That's equal to the mass times little g, but we don't know the mass. We do, however, know the density. And we talked about this a little before. The mass density is equal to the mass over the volume, just like the volume charge density is equal to the charge over the volume. So density Mass density is mass over volume. Charge density, if it's volume, charge density is charge over volume. So the mass and the charge are playing the same role here. And look at this, we have forces here, which is a charge times a field for the electric force and a mass times the field for the gravitational force. So in this equation, the charge and the mass are playing similar roles also. Isn't it beautiful? Okay, so I want the mass. I have the density. I don't have the volume, but I can find it because an oil droplet would be a spherical shape. And the volume of the sphere is 4/3 pi r cubed. So if I solve this for the mass, I get the mass is equal to 4/3 pi r cubed times the density. And remember that they're giving us the radius and the density, which makes our life harder here, but they're doing it for a specific reason, and that's because in the experiment, the radius is what you can actually measure, not the mass. Okay, so I can put this in for the mass. So this is 4/3 pi r cubed times the mass density, and then that was the mass. This is times little g. What am I looking for here? I'm looking for the charge on the oil droplet, so I just have to divide by sigma over epsilon naught. The epsilon naught, I could multiply it by that to get it over to the other side, and I can say the charge is equal to sigma goes in the denominator on the other side, epsilon naught goes in the numerator on the other side, so this is epsilon naught over sigma times 4/3 pi r cubed times the mass density times little g. This is supposed to be a symbolic answer, so it's going to be like this, and that's it. From this, we can find the charge. Now, let's look at the things which could actually change depending on which oil droplet you're looking at. Epsilon naught is a constant, and that is related to K, so that's not going to change. You could change the charge density on the plates, but it would be the same for all the oil droplets. And R is going to change, and Q can also change. So for different oil droplets, the radius and the charge would change. This is the mass density for an oil droplet, which is going to be the same for all the oil droplets, and G is not going to change either. So if you spray a bunch of oil droplets in between the two plates, they'd have different radiuses and different charges, but everything else in this equation would be the same. Now, if the radius is different, then depending on the charge that you have on that oil droplet, it might not be suspended when this oil drop is suspended. So only some of the oil droplets are going to be suspended at this value of sigma. But you could change the charge density to balance or suspend different oil droplets, which is what Robert Millikan did. Okay, so now let's talk about his experiment. So you can spray oil droplets in between the charged plates here. Pick one oil droplet to focus on. You would need to measure the radius of that oil droplet, and you can change sigma, which would you could change by changing the voltage between the two plates. So you can change the charge density to suspend that oil droplet, and when this oil droplet is suspended, this is true, and you can plug everything in here, your charge density and your radius and all these other things that don't change to get the charge. Then you could pick a different oil droplet, which might be suspended at a different value of sigma, plug everything in here and get that charge. Now, when Millikan did this experiment, he showed that charge was quantized. So after looking at a bunch of different oil droplets, he noticed that all the charges that he got were multiples of E. So you could get E, or 2E, or 3E, and you could actually get negative values also, and so on, but they were all multiples of the elementary charge. Now, we know that is equal to 1.602 times 10 to the negative 19th. And we know that this is the absolute value of the charge on the electron. So depending on whether the oil droplets were missing electrons or had extra electrons and how many electrons they were missing, that would tell you what the charge was. Now, the interesting thing is, when Millikan did this experiment, he did not have the correct value for the, hang on a minute. He didn't have the correct value for the viscosity of air, which actually doesn't appear in our equation. But we're not going to be worried about that because we assume that everything takes place in a vacuum. And he actually did the experiment a little bit differently also. So rather than suspending the droplets, you could also have them fall and reach terminal velocity. So that's where the viscosity of air comes in. And if you're interested in knowing more about this experiment, if you take Physics 262 here at MCC, one of the labs is actually the Millikan oil drop experiment. However, our Millikan oil drop experiment has been leaking oil, and so rather than doing the actual experiment, we've been doing a simulation. But if you take Physics 261, you get to do that simulation and learn more about the Millikan oil droplet experiment. So he actually got the wrong value, and now it's time for the first installment of Story Time with Professor Moore. And today's story comes from Surely You're Joking, Mr. Feynman. And this was written by Richard Feynman, who is a famous physicist. And here we see, we have learned a lot from our experience about how to handle some of the ways that we fool ourselves. One example is that Millikan measured the charge on an electron by experimenting with falling oil droplets. So here they tell you it's falling oil droplets, which would be when they reach terminal velocity. There's two different ways you can do the experiment. The other way is with the oil droplet suspended, like it was in our problem. And he got an answer which we now know not to be quite right. It's a little bit off because he had the incorrect value for the viscosity of air. It is interesting to look at the history of measurements of the charge of the electron after Millikan did his experiment. If you plot them as a function of time, you find that one is a little bit bigger than Millikan's, and the next one a little bit bigger than that, and the next one's a little bit bigger than that, until finally they settle down to a number which is a little higher. Now, why did this happen? Because if he had the wrong value for the viscosity of air, as soon as someone else did the experiment with the correct value, they should immediately get back to the correct value of E, which is 1.602. But it didn't happen that way. Instead, it slowly approached 1.602 as more people did the experiment over time. So why didn't they discover that the new number was higher right away? Unfortunately, this is the thing that scientists are ashamed of, this history, because it's apparent that people did things like this. When they got a number that was too high above Millikan's, they thought something must be wrong, and they would look for and find a reason why something might be wrong. When they got a number closer to Millikan's value, they didn't look so hard, and so they eliminated the numbers that were too far off, and they did other things like that. And we might have seen examples of this in our Coulomb's Law lab. If there were numbers that didn't fit the trend line, then sometimes we go back and we retake data for those numbers, but that can get you into trouble. Okay, so that's Story Time with Professor Moore from Surely You're Joking, Mr. Feynman. And now we're going to move on to Part B, where we're actually going to plug in some numbers. So all we're doing for Part B is we're taking this, and epsilon naught is equal to 8.854 times 10 to the negative 12th Coulomb squared per Newton per meter squared. So that's epsilon naught over sigma, which they're going to say here is 1 times 10 to the negative 6th coulombs per meter squared. So that's epsilon naught over sigma. Then we have 4/3 pi, and what is the charge on a radius of 1.8 micrometers. So that's times 10 to the negative 6th meters. And remember, the radius was cubed. And the oil droplet has a density, a mass density of 0.835 grams per centimeter cubed. Why do they do this to us? I have to change the grams to kilograms. When I change the grams to kilograms, I get a times 10 to the negative 3rd. And when I change centimeters cubed to meters cubed, for each centimeter, I got a times 10 to the 2. So all together, that would be times 10 to the 6th. This is kilograms times meter cubed. And I ran out of room for my 9.8 meters per second squared. So if we have everything in kilograms, newtons, meters, coulombs, seconds, the units will all work out, and we get this is 1.77 times 10 to the negative 18th coulombs. And that is our answer. Problem number 35 is similar to this, and it's a homework problem, but 35 is a little bit easier because they are letting you use the mass in problem 35, so you don't have to use an equation like this. Okay, so that concludes problem 36.